Hey everyone, this is the second lesson on Abstract Algebra. Today we're going to be talking about different properties of abstract groups, the definition for a subgroup, the order of a group and order of elements in a group, and then several examples that hopefully will be helpful for your understanding. So just to start out, last time we defined abstractly what a group is. Basically it's a set, G, and a multiplication law is what it's called, or an operation, dot, and it has some requirements for it. First, you need that the multiplication law is associative, so usually we just call this the associativity law. Then you need to have a 1 or an identity in the set, such that for any element, if you multiply 1 by that element, nothing happens. This is the same way you think about 1 in the real numbers or the integers. And this is usually called the identity law. And then you have, for all elements G, there is a G inverse, such that G times G inverse is the identity. So this is usually called the inverse law. So basically a group is something that has associativity, an identity, and inverses for every single element. And that's basically all you need to know. Today we're going to give some practice of using these laws for a group to prove some extra facts about them. So first we're going to figure out some nice properties that come with groups. And we're going to prove each of these. There's about 4. So first of all is that the identity in G is unique. And if you're kind of confused what that means, we'll get to the proof and I'll explain it there. So the second one is that for all elements G in G, the inverse element, which we know exists, is actually also unique. And there's a way of writing there exists a unique. It is like this. So the exist sign and then the exclamation point afterwards means there exists a unique G inverse in G. Okay. Third rule is that the inverse, hopefully this is kind of obvious, but the inverse of G inverse is G. And then finally, the last one is that the inverse of multiplying 2 elements together is H inverse times G inverse. Hopefully some of these, when you think about them, are relatively straightforward, but we'll prove all of them rigorously. Okay. Starting with, well, let's just say proof. Starting with number 1. Okay. So to prove something is unique, it means it's the only one that exists. And if there's other ones that do exist, it's actually just equal to the first one. So let's assume that there are 2 identities. Let A and B in G be identities. And this just means when you multiply anything by it, you get the same thing. Okay, this implies that we then have, what happens if I multiply them together? Well, A times B, if I use let's say I'm thinking of A as the identity here, then A times B doesn't change B, so I get B out. But now if I look at A times B and I think of B as the identity, so I was kind of thinking of A as the identity here, B as the identity, A times an identity doesn't change A, so you get A out. But this is the same expression, so this then implies that B equals A. And so thus they're really the same thing. Thus the identity is unique. Also, if you're curious, this little square symbol means proof done. Okay, proof of number 2. We want to show that the inverse is unique. So let's let G be a group element and assume that A and B in G are inverses of G, which means that like G times A equals 1 and G times B equals 1. Okay. So what we're going to do is we're going to kind of exploit, in some way you have to exploit that both A and B are inverses of G. So the first thing I'm going to do is I'm going to write A equals A times 1. Of course, nothing has changed here because 1 does nothing. But since B is an inverse of G, I'm going to write 1 as G times B. But then by the associativity law, so this was just inverses. If I'm writing out the steps here. But by the associativity law, I can actually move around these parentheses and switch this to A times G times B. So this was associativity. And then finally, since A is an inverse of G, I know that this becomes 1. So this is 1 times B equals B. But then that implies if you just follow the series of equal signs, that A equals B. Which means that these inverses were actually unique and were the same thing all along. Okay, great. And if these proofs seem a little unnatural, that's because kind of when you're starting off doing this abstract algebra stuff, it's kind of just using the symbols and the definitions. Eventually this will get way more interesting and the proofs will get way more unique, and it's not just about, oh, associativity, then inverses, then X, Y, and Z. Okay, let's prove number 3. But you kind of have to start out this way. Okay. So this one is actually not so bad. We're trying to prove that the inverse, we want to show, WTS means want to show, that the inverse of G inverse is G. So this just means we want to show that the inverse of G inverse is that element, let's call it H, such that H times G inverse equals G inverse times H equals 1. But if you just think about how G inverse is defined, it's defined as that element such that G times G inverse equals G inverse times G equals 1. So clearly, if I replace H equal to G here, I get this to be true, which means that G is the inverse of G inverse. And if you're curious, I can apply the thing I just proved, number 2, to say that this inverse is unique. So G is the unique inverse of G inverse. Okay. That's a neat trick for proving something as an inverse. If I just find something that works, then I know it's the only one because the inverse is unique. Okay. So now we're trying to prove, if I let G and H and G, I want to show that G times H inverse equals H inverse times G inverse. Okay, same trick. I'm just going to show that this thing works and then say by property 2, it's unique. So let's look at G times H times H inverse times G inverse. Well, by using associativity, I can group this as G times H inverse times G inverse. But H times H inverse is 1, so then I really just get G times G inverse, and then that's 1. And of course you can see, try on your own, if you flip the other way around, it'll just be G inverse G on the middle, and then H and H inverse on the outside. You get the same thing. And since by 2, inverse is unique, this is the only inverse. This is the inverse. That's a just subtle kind of grammar there. Since it's unique, you can say it is the inverse instead of it is a inverse or an inverse. Okay. So that was the proof of all of our properties. Great. now we're going to get onto some definitions or helpful definitions for groups. Helpful definitions. Okay. The first one we defined last time, but I'll do it slightly more rigorously. So let G, dot be a group. Many times we'll just describe this group as just G, which, to be fair, as we discussed, doesn't actually make that much sense because you need to define a group with a set and a multiplication law. But just to make it easier, if the multiplication law is assumed, as it is here, then we just use the word G, or the letter G, to define the group. Okay. Let this symbol denote the size or number of group elements. And usually this is called the group order. Group order. And it's kind of like an absolute value symbol around the group. And just an example that we saw last time was that the order of D3 equaled the order of S3 equals 6, because there's 6 group elements in each of these groups. Okay. Another definition. This one is going to, instead of define the order of a group, the order of elements in a group. Okay. So now I'm going to just write let G be a group. And then let G be some group element. The order of G is the smallest positive integer. Note I said positive. Smallest positive integer such that G to the n equals 1. And that this integer I'm calling n. Okay. And note when I write G to the n, I'm saying G times blah, blah, blah times G, all of this n times. So it's n, the order of a element is the smallest positive integer n, such that if you multiply the element n times, you get back to the identity. So let's see some examples to understand what this is saying. Okay. So consider the rotation element in D3. We know that r cubed equals 1. If you rotate the triangle 3 times by 120 degrees, you get back to the identity. So this means that the order of r, usually denoted ordered r, equals 3. Because no smaller power of r is going to get you back to the identity. You should also note that you also get something like r to the 6th equals 1, and r to the 9th equals 1, so on and so forth. But we don't say order of r is 6 because the smallest positive integer where this is true is 3. Now take s in D3. We see that s squared equals 1. And this means that the order of s equals 2. Great. And note, you might say, oh, I could just take anything to the 0th power and it'll be the identity. But my definition says take the smallest positive integer. Okay. Now, just 2 more definitions. I'm going to define a subgroup, which I also introduced last time. Let G be a group. A subgroup of G is a group H, which can be more rigorously defined as H, comma, the same multiplication law as G, or this one is G, comma, this dot, and H is a subset of G. So what this is saying is a subgroup is something where you take a subset of the group elements, call it H, and you keep the same multiplication law. If this is a group, it's a subgroup. It's just like a smaller group inside of a larger group. And just a quick note here. There's an easy way to prove that a subset of group elements forms a subgroup. So H, and also when we're saying that something is a subgroup, we usually write it, some people write it like this. I kind of like writing it like this, but I think usually the standard notation is doing something like this. So this forms a subgroup when H is closed, I'll tell you what this means, under the multiplication and inverses. Okay. So what this means, oh yeah, and of course it has to have an identity. And identity. Of course that doesn't follow from these two, but I'll get to that. So basically, if H needs to be a group, it needs to satisfy all the regular properties that G satisfies. It needs to have an identity, needs to have inverses, and needs to have an associative multiplication. Now, the problem is with just choosing a subset of elements is that you don't necessarily know that if two of them are multiplied together, that it'll stay in the subgroup. So let's take, for example, I'll do this example later, but it's good to introduce it now. There's a subgroup 1, r squared in D3. Now, in this subgroup, if you multiply any two elements, you get back to the same thing. But imagine I had an extra s in here, 1, r squared, and then the s. This, I claim, is not complete, because I can do r times s, and that's not any of these elements here. So, clearly it's not closed under multiplication, and it can't form a group. The other thing you need is that you need to have inverses. And so what that means is that every element in the group, of course, subgroup, has to have an inverse. And this also implies that you have the identity, because if you have r and r inverse, then r times r inverse is the group because it's closed, and r times r inverse is 1. So 1 is in the subgroup. So that's just a quick way of determining if something forms a subgroup. Check if it's closed under multiplication and it has inverses of every element in the group. Okay. Final definition. A group G is abelian if for all pairs of elements G and H in G, G times H equals H times G. And if you don't know what this means that all elements, there's a word for this, all elements commute. And that's basically what it means for a group to be abelian. Okay, so let's get back to that example I just introduced above here. So note, when we were talking about R in D3, we said that the order of R was 3. Okay, well, I would claim that that actually lets us create a subgroup, H, which is 1, r squared. And note, I can't go further. I can go to r cubed because that's just the same as 1. And r to the 4th is just r, and r to the 5th is r squared. Now, I know this is a subgroup because one, well, every element has an inverse. For example, the inverse of r is r squared is r, and the inverse of 1 is just 1. And I know it's closed under multiplication because if I multiply r times r squared, I just get r cubed, which is 1. And you can see for multiplying any two other elements, you're just going to get something. It's because anything in the group is just a power of r. So if you multiply anything together, you just get another power of r. Okay. Finally, you should see that H is abelian. Okay, why is this the case? Well, let's just try some of the elements. If I take r times r squared, I get r cubed. But this is the same thing as doing r squared times r. So maybe you see why it's abelian. It's because, like I said before, if you multiply any two elements, it's just another power of r. But if you just have a long series of r's, it doesn't really matter how you order them. You're still going to get the same thing at the end of the day. Because of this, all elements commute with each other, so H is abelian. Now I should note that D3 itself is not abelian. And you should check this for yourself. And I'll give you a hint. The best way to check it is to determine whether SR equals or doesn't equal R times S. And I'll tell you that they're not equal to each other. But just try this out. And note that if they're not equal to each other, then there is an element that doesn't commute, which means it violates the definition of abelian, which requires that all elements commute with each other. All pairs of elements. Okay. Now let's do some helpful examples for groups. So we already saw D3 and S3 last time. Saw D3, S3. Maybe a little exercise for your own enjoyment is to find the order of elements in these groups and find maybe some subgroups. If you would like to, try to use the trick I showed up here, whereas if you have an element that has order 3, you can define a subgroup that has all the powers of that element up to 3 minus 1. Or if the order is n, up to n minus 1. Okay. Now let's get to some other examples. And we'll actually prove that these are groups. So let's take our set of elements to be the integers. That's what Z stands for. And our law, multiplication law, well, multiplication is going to make it confusing, but I'm going to define it as addition here. And let's just call this group G. So first of all, we know plus is associative. We also know that there's an identity element. If you can guess what it is, it's 0, because anything plus 0 is just the same thing back. So for all n and z, n plus 0 equals n, so 0 is the identity. And then for all n and z, now we need to show inverses. There exists negative n in z, such that n plus negative n equals 0. Of course, in the integers, we have the positive and the negative integers. So for every positive, there's a negative 1, which is its inverse, according to plus. And for every negative 1, there's a positive 1, which is its inverse. Great. So it's clear that this thing is a group. It satisfies all the group laws. Now let's look at some of our definitions we defined. The order of our group is going to be the number of set elements, but since Z is not finite in size, this group has infinite order. Also, if we look at any element or any integer that's not equal to 0, the order of that integer is also infinity. The reason why this is the case is because if you just add anything to each other, it never goes down to 0, it just keeps on increasing. So if you looked at n equals 2, it just go 2, 4, 6, 8, so on and so forth, and never go down to 0. Of course, if n does equal 0, then the order would just be 1, because you just 0 added to itself is 0. Okay. Finally, let's look at some subgroups. So, take a positive integer, n, and consider the set or the subset hn equals 0, negative n, negative 2n, and that keeps on going down, and then positive n, 2n, 3n, and that keeps on going up. So this is basically anything of the form k times n, where k is an integer. And my claim is that hn is a subgroup of G. Let's see why that's the case. Well, we see that it's closed under the law, or addition, because if you have k times n plus m times n, then this just equals k plus m equals times n. But of course, this is the form of something in the subgroup. Then we also see if we have k times n in hn, then negative k times n is also in hn, and k times n plus negative k times n equals 0. So every element has an inverse. So we've shown that hn is a subgroup of this group. Great. Once again, you can just think of this subgroup as all multiples of some integer n. Okay, let's look at something that's a little more interesting. In this case, every element basically had infinite order. So let's look at something where no element has infinite order and they all have finite order. So take the set 0, 1, all the way to n minus 1 for some integer, positive integer n. And then this special multiplication, addition, which I will define in a second. And we're going to call this group Z mod n. This means Z mod n. Sometimes this will also be written as Z mod nz, and maybe we'll explain why this term is used at a later point, but you need to understand rings and ideals before you can understand that definition. Okay. So, let's define this addition. Take two numbers a and b in the set 0, 1 to n minus 1. And a, o plus, and b equals a plus b mod n. So you just take the remainder of a plus b mod n. That's all it means. That's just what I meant by this special symbol here. And also probably makes more sense why I'm calling this Z mod n. Okay, so first thing we see is that this operation is associative because it's basically just the same as regular addition. We also see that we have an identity. When you add 0 to any other group element, nothing happens. And finally, we have take some a in Z mod n, then consider the element n minus a in Z mod n. So if a is 1, consider n minus 1. In this case, if a is 0, n minus 0 is n, which is 0 mod n. Well, we see that a plus, or I should use o plus n minus a, equals a plus n minus a mod n equals n mod n is equivalent to 0 in z mod n. Okay. So we just shown that every element has an inverse because there's something when you add them together, you get 0. So this is in fact a group, and let's look at some of its properties. First of all, the order of the group is n. So something you can notice is that now we've just found a way to define a group of any integer order. If you give me some positive integer, maybe it's 1,000,000, I can create this group z mod 1,000,000 that will have 1,000,000 elements. We also see that the order of some element A is more interesting, and in fact will depend on what n is. So we do have one case, which is that we know order of 1 is n. This is because you get 1 plus 1 plus 1, you need to do that n times, so eventually you get to 0. But the order of other elements is more interesting, and I'll leave that as an exercise. So the reason why the order is interesting is, like I said, it depends on what n is. So I want you to try finding subgroups of let's say z mod 12. So this is when n equals 12. And then also try it for some prime number. You can try a specific one like 5 or 7, but you can also just think that z mod p, where p is some prime number. And try to find subgroups and order of elements. So I'll just give you an example. The order of, let's say 2 in z mod 12 is 6, because you need to add 2 6 times to get to 12. Okay. Okay. This will be our base, our last example, EX3. This will be a little more challenging, but should hopefully give you an idea of the power of this definition of groups. So let m by n of R denote the matrices M such that M is a n by n matrix with entries in R and determinant of M is not equal to 0. And there's a very specific reason why I've chosen this requirement right here. Determinant of M is not equal to 0. And we'll get to that later. So it's all m by n matrices with real entries where the determinant is non-zero. Hopefully, if you have some experience with linear algebra, you might see why I've defined it that way. So let's define our group. It's going to be, the set is going to be this m n cross n of R. And our multiplication law is going to be matrix multiplication, which I'll define by this x. And I'm going to call this group the general linear group for n by n matrices with entries in the real numbers. So GLNR. This GL starts for general linear group. So just first couple things, the matrix multiplication is associative. We also see that there's an identity, which is the identity matrix. Oops. This is in GLNR. And if you do any matrix times this, you get the same thing out, because it's the identity. And we see this is in GLNR because the determinant of this thing is 1, which is not equal to 0. finally, this is the interesting property. For all matrices M in GL and R, we see that the inverse of M must exist. So you might know from linear algebra that sometimes matrices don't have inverses. In this case, M inverse exists because determinant of M is non-zero. This is equivalent to saying it has an inverse. And in fact, you might know that determinant of M inverse must also be non-zero because, well, it has an inverse M. So, since determinant of M inverse is not zero, M inverse must be in the general linear group. And this proves that this thing also has inverses, so it satisfies the definitions for being a group. Okay, great. Some quick notes is that the order of this group is, of course, infinite. We can define the order of certain elements. For example, if we let M to be a rotation, maybe you can think of this when n equals 2, then the order of M just equals the number of times you need to rotate to get back to 0 degrees, or to do a full 360. So for example, if it's a rotation by 20 degrees, you need to rotate 18 times. So the order of M would then be 18. Great. Okay, so hopefully those examples were helpful for better understanding the definition for a group and also getting to practice some extra definitions and properties that we've defined in this lesson. And I just want to give you a quick exercise to do on your own, which is let S1 be defined as the complex numbers in C such that the order of that complex number is 1. And try to prove that S1 with regular multiplication of complex numbers is a group. So this will be a good exercise at using the definitions and is kind of interesting as well. Okay, thanks for watching.